So in this question, again, we're given some more data, and we may as well be writing that down as we're reading through the question. So we have a stone on a string with a radius of 80 centimeters, which is the same as 0.8 meters, converting these to a SI base units. We have a mass of the stone of 90 grams, which is equal to 0.09 kilograms, and it also told that it completes 10 revolutions in 8.2 seconds. In part A, we're asked to find the time taken for one complete revolution. Well, I like to view this as a bit of a ratio. We have 10 revolutions to 8.2 seconds, and if we wanted to find one revolution, we're dividing this by 10. So we can divide this by 10 and get that one revolution is 0.82 seconds. And one revolution then be the period. Part 2. We're asked to calculate the distance travelled by the stone during one complete revolution. Well, if it's going around a circle, and we know that there's an equation that tells us the distance around the circle, the circumference of the circle, which is the distance will be 2 pi r, the circumference of the circle. Substituting our value in for r, the radius, to be 0.8, we can then type that onto a calculator and it may give us a result of 8 pi over 5 meters, or as a decimal answer, 5.02, and so on, meters. Part 3. We're asked to calculate the speed of the stone as it travels in the circle. Well, here we have a distance, we have a time, and so quite simply, the speed can be said to equal distance over the time, or 8 pi divided by 5, all over 0.82, and that will give you a result of 6.13 meters per second, quoted to 3 significant figures. Part 4. We're asked to calculate the centripetal acceleration of the stone. Well, we have a velocity, we have a radius, and so we may as well use the equation centripetal acceleration equals v squared divided by r, substituting in our values like so. I've been using the unrounded version on my calculator, all divided by r, which is 0.8. If you put that into a calculator, you'd get an answer of 47.0 meters per second, quoted to 3 significant figures. Part 5. We're asked to find the centripetal force. We have an acceleration, we have a mass, then we'd have an equation of F equals ma, substituting in our values. 47.0, and so on. Type that into a calculator and you'd get the answer of 4.23 newtons, quoted to 3 significant figures. And that was all for part A. So in part B here, we're asked what provides a centripetal force. Well, we have the string here. We'd have then, if I just do this in black, we'd have a force exerted on the stone by the string, and that would be tension. And so that tension will be, in this case, providing the centripetal force. and only the centripetal force, because this is planar. It's completely flat, it's at right angles, so the weight is at right angles to the force of the string, and so that doesn't come into play. So here we'd have then the tension due to the string. Let's see. What is the angle between the acceleration of the stone and its velocity? Well, because this is flat, we can model this in 2 dimensions. Say this is the orbit of the stone. The stone may be at a point here. We know that the centripetal force and acceleration both act inwards. Let's say that's the centripetal force. What would be the velocity? Well, the velocity is sometimes dubbed tangential velocity or the linear velocity, i.e. it goes off like so, and thus there'd be a right angle there, and that is 90 degrees. And that's because this is completely flat. You may be wondering, is this actually possible? Can you spin around this stone in a completely flat circle, a horizontal circle? And the answer is no, you need infinite energy for that.